So let's work through the final exam review for business stats. So this first question, if you think all the way back at the start of the semester, you were always given information and then you had to figure out the minimum number of classes, your class width, and then determine what your classes would be. So we're going to do a practice problem like that now. So to do that, we need to know the maximum number, the high number of our data set, the low number, the minimum, and then how many pieces of data are in our data set, right? So our N, or our sample size, is 72. So the first thing we want to figure out, the minimum number of classes. So our minimum number of classes will be using this formula. 2 to the C power is greater than or equal to N. So our N, we already said that was 72. C is your minimum number of classes. So this is going to have to be like a trial and error sort of thing. So 2 to the C is greater than or equal to 72. So we have to just see, okay, 2 to the second power, 2 to the third power, until we reach 72. So 2 to the seventh power will be the first time that we exceed 72. Right, so C equals 7. Now this is the minimum number of classes. This is not your definitive number of classes. This is just how many you need as a minimum. You can go up by 3. So we could have anywhere between 7 and 10 classes for our data set. So we can use this minimum number of classes that we found to then figure out our approximate class width. Right? So our approximate class width, if we take a look at a formula, we'll be able to see that as max minus min over the number of classes, right? Or high minus low, based off of the wording of this question. So high minus low, 795 minus 114 over 7. That 7 is what we just found our C to be in the last part. So if we do this, we get a class width of 97.286. Now, there's a few problems here, right? It's not a pretty number at all. There's decimals. 97 by itself isn't even a pretty number, right? So we need to make this a pretty number. And to be thinking about pretty numbers, we can be thinking of like coins, right? So if you could work mostly with like, 5, 10, 25, 50, 100, those are pretty numbers. So let's just round up to 100, right? As long as we have at least 7 classes, this will be okay. So our class width that we're going to go with is 100 because that's the closest pretty number for us. So now we have to determine our classes. We know our number of classes, or our minimum number of classes, and we know our class width that we're going with is 100. So our first class starts at 100 to 199.99. Now, why didn't we start at 0? Because if we started at 0, we wouldn't have had any pieces of data in that first class. Because that first class would have been 0 to 99.99. And the smallest number that we have is 114. So there would have been no purpose to have a class less than 100. Now, why do we have the decimals? Well, our classes have to match what our data tells us. So since our data has 2 decimal points, our classes have to have 2 decimal points. If our data was just 795 and 114 without the 38 and 54 cents, our classes could just be 0 decimal points. But we can't do that here. They need to match our data. So that's our first class. Then we have our next class, our next one. Then we go in the 400s, the 500s, the 600s, and then our final class is 700 to 799.99. And how do we know that that's our final class? Because that's the class that would hold our maximum number, our high number in this case. Right? So the first class is where your low will be, and your last class is where your high will be. Now, you count your number of classes here, and we have 7. Right? So we are okay there. Again, we could have gone up by 3 in case we would have needed it. So that's your number of classes, your class width, and your classes themselves. Now again, why do you do all this? You do this to create a frequency, relative frequency table, right? So your frequency is how many times does a number in each class show up in your data set. Relative frequency would be that frequency number that you found divided by your n, divided by 72. So that way we could say, okay, numbers between 100 and 199.99, well, that's 13% of our total data, right? That's what our relative frequency would help us find. So that's question number 1. Question number 2 is asking us to calculate the standard deviation for the sample below. So we're given a list of data points, right? 7, 18, 15 from a sample, and we need to find our standard deviation. So remember, you have a couple different types of standard deviation, right? You have population standard deviation, and then you have sample standard deviation. Here, we're looking at sample standard deviation, so that's S. Population standard deviation, that's sigma. So we're not dealing with a population here, though. So we're dealing with a sample, so our formula is there. It's the square root of the sum of x minus x bar squared divided by n minus 1. So we need to take this data set and put it into our list. So we set up our 3 lists. We have our x, x minus x bar, and x minus x bar squared. In your x list, that's your data points. That's the information that was given to us right there in the problem. Right? So that's what we're going to plug into our x list, our x column. And then our next list is x minus x bar. So we need to find our x bar. Again, x bar is your sample mean, right? So that's the average of all of our x's. So if we take the average, we'll find that our x bar is 13.75. So x minus x bar now will be each individual x value minus 13.75. So we take 7 minus 13.75, 18 minus 13.75, and we end up with these values. Now, if you're doing this in the list in your calculator, you can go up and highlight L2 at the very top and type L1 minus 13.75, hit enter, and that will populate this list for you. Now you'll notice there's some positive numbers and there's some negative numbers. Those negative numbers are why we now have to square that last list, right? Because we want to get rid of those negatives. So we're going to now do our x minus x bar and square it. So negative 0.675 squared, 4.25 squared. We keep going down the list and we will end up with these amounts. And you'll notice there are no negatives, because when you square a positive, or when you square a negative number, you end up with a positive, right? So if you end up with any negatives here in your third list, you'll need to take a step back and figure out what happened. So if we think back to that sample standard deviation formula, we needed the sum of x minus x bar squared. So let's take the sum of this third list. So if we take the sum of this, we get 339.50. So we can use that in our standard deviation formula. So that's going to be the numerator, right? That's the sum of x minus x bar squared. And then that has to be divided by n minus 1. Well, our n is our sample size, right? So we count how many values we have, and we have 8. So n is 8. So we plug in our numbers. So your sample standard deviation is the square root of 339.50 divided by 8 minus 1. You do that math, and you'll end up with 6.9642. Now, if you forget to square root it, you found something. You found the sample variance, right? S squared is your sample variance. The square root of the variance is your standard deviation. And that's what we were looking for here. So now we can move on to question number 3. So question number 3 says there are 65 hotels in the city. After researching them, you found that 51 of the hotels have positive reviews online. 55 of the hotels in the city offer free Wi-Fi, of which 48 have positive reviews. We need to then find the probability of a positive review, the probability of no free Wi-Fi offered, the probability of a positive review and free Wi-Fi, the probability of a positive review or free Wi-Fi, and lastly, the probability of a positive review given free Wi-Fi is offered. And then once we find those 5 probabilities, we can answer the question, are positive reviews and free Wi-Fi independent events? So, to figure out these probabilities, we are going to need a chart. So we have some information that was given to us, right? We have 65 total hotels in the city. So that's going to go into our grand total. So this chart is going to have positive and negative, right? Positive reviews and negative reviews. And then free Wi-Fi and no free Wi-Fi. So those are our different variables in this situation. right? And then we just start plugging in the numbers that we know. So that's 65, the grand total, right? The total number of hotels in the city. And then they said, after researching them, you found 51 of the hotels have positive reviews. So the total for the positive reviews is 51. 55 of the hotels in the city offer free Wi-Fi. Okay, so the total for free Wi-Fi is 55. Of which 48 have positive reviews. So of those 55 that offer free Wi-Fi, 48 of them have positive reviews. So we put that 48 at the intersection of positive and free Wi-Fi. Now, we have enough to start filling in the rest of the chart. No Wi-Fi, that's going to be 10. Since there's a total of 65 hotels, 55 of them offer free Wi-Fi. So that means the other 10 don't. Right? So we put that 10 there. Negative reviews, we get 14. There's a total of 65 hotels. 51 of them have positive reviews, which leaves 14 hotels to have negative reviews. Hotels that have positive reviews with no Wi-Fi, that's going to be 3. Because there's a total of 51 with positive reviews. 48 of those offer free Wi-Fi. So the 3 that are left over do not. Now, no Wi-Fi and negative reviews, there's 7 of those. Right? Because a total of 10 hotels do not offer Wi-Fi. 3 of those hotels had positive reviews, which left 7 to have negative reviews. Now, free Wi-Fi and negative reviews, there's 7 of those. There's 14 total hotels with negative reviews. 7 did not offer Wi-Fi, so that means that the other 7 do offer Wi-Fi. So once we have this table all filled out, then we can work through finding all of those probabilities. So the first one that we wanted to find was the probability of a positive review. So we have a total of 51 positive reviews. There's 65 hotels in the city. So 51 divided by 65 gives you a probability of 0.7846. Now, probabilities have to be between 0 and 1. So if they're looking for a probability, they're looking for 0.7846. This could also be asking for what's the percent chance of a positive review. In that case, then you would turn it into a percentage and say 78.46%. But when they're just looking for probabilities, we keep it in this original decimal form. So now the probability of no Wi-Fi being offered. Well, we take a look back up at our chart again. 10 hotels do not offer Wi-Fi, and there's 65 hotels in total. So we go 10 divided by 65. 10 divided by 65 gives us a probability of 0.1538. So that's the probability of a hotel not offering Wi-Fi. Now, the probability of a positive review and free Wi-Fi is offered. So we take a look up at the table and we see, where do the positive and free Wi-Fi intersect? Well, that's our 48, right? So 48 out of 55. Our denominator remains the total amount until we get to the givens at the very end. So we go 48 divided by 65. So the probability of a positive review and free Wi-Fi, that's going to be 0.7385. What about the probability of a positive review or free Wi-Fi being offered? So we need to think about all of the options here, right? So we just take a look at the positive review. For positive reviews, there could be that 48 or that 3. And then free Wi-Fi, there's the 48 and the 7. Well, we don't want to count the 48 twice, right? We only want to count that once. So we'll do 48 plus 3 plus 7. All of that divided by 65. So 58 divided by 65 gives you a probability of 0.8923. So there's a pretty good chance, if you just pick a random hotel in this city, that it's either going to have a positive review or they're going to offer free Wi-Fi. Now, finding our last probability here, the probability of a positive review given free Wi-Fi is offered. When we have a given like this, that given becomes your denominator. So the total for the free Wi-Fi is your denominator, that 55. Your numerator is the probability of a positive review, just taking a look at that free Wi-Fi population, right? We're only looking at that free Wi-Fi column. We forget about all the other numbers. So we go 48 divided by 55, and the probability of a positive review given that free Wi-Fi is offered is 0.8727. So we found all of our probabilities. So now, the last part of this question was asking us, are positive reviews and free Wi-Fi independent events? And then it wants us to prove. Well, if the probability of A equals the probability of A given B, they're independent. Right? So the probability that it's Wednesday equals the probability that it's Wednesday given my name is Stephen. Right? So those two events, totally independent. It doesn't matter what day it is. So, in our case, we have to consider, does the probability that a positive review equal the probability of a positive review given free Wi-Fi? So we found over in part A, the probability of a positive review equals 0.7846. The probability of a positive review given free Wi-Fi is offered is 0.8727. So they don't equal, which means they are dependent, which would make some sense here, right? So if free Wi-Fi is offered, is going to play a role in if it's a positive or negative review. So these are dependent events. So when they want you to prove, the proving part is to show that they do not equal. So now question number 4. It says the average price for a plane ticket is $225 with a standard deviation of 15. We need to find the probability that a plane ticket costs more than $240, less than $195, and between $210 and $240. So we're going to be using the empirical rule in this problem. So we draw our bell curve, right? And in the very middle of our bell curve is our mean, our average price for a plane ticket. So that's our 225. And then we have 3 standard deviations on either side of our mean. So we add and subtract 15 to figure out our values at each standard deviation, right? So one standard deviation to the right is 240, right? We added 15. We add 15 again, we get 255. If we were to subtract 15 from our mean, we would get 210. Subtract 15 again, we get 195. So now we can think about the empirical rule. And the empirical rule tells us that within plus and minus 1 standard deviation is 68% of your data, right? That's the largest group, the middle part of your bell curve. Then between plus and minus 2 standard deviations is 95%. And then plus and minus 3 standard deviations is 100%. So that's going to help us when we have to find the probabilities of plane tickets. But there's something that could help us even more. If we break this apart into what each individual section of the bell curve is right now, right? Because we've broken up this bell curve into 6 different sections. So if we figure out what each individual section holds, it's going to be even easier to figure out our 3 probabilities. So between plus and minus 1 standard deviation is 68%. A bell curve is symmetrical, so each of those sections is 34. Now, between plus and minus 2 standard deviations is 95%. But we don't want to worry about that 68, so we do 95 minus 68, and that gets us 27. So now we need to split that 27% across the 2 different sections, so we get 13.5 for each of those. And then we need to split the final 5% across. So each of those sections at the very end are 2.5% each. Right, so we just broke down the empirical rule a little more. And then that way we can figure out the probability between any of the points here, right? Between 195 and 270. Between 210 and 255, right? It's a lot easier to figure that out that way. So we'll keep that there as we go through this. So the probability that a plane ticket costs more than $240. So that's 240 and to the right. So we see that that's 2 different sections. That's 13.5% and that's 2.5%. So we want to add those together. When you take 13.5 plus 2.5, you'll get 16%. Now, remember, we already touched on this a little bit earlier. Percentages are different than probabilities. So if they want to know the percent chance that a plane ticket costs more than $240, that's 16%. However, they're asking, what's the probability that a plane ticket costs more than $240? That's when we need to turn our percentage into a decimal. So 16% as a decimal is 0.16. Now, part B, the probability of a plane ticket costing less than $195. So we find $195 over on the left side of our bell curve, and we want less than. Well, that's just that single section of 2.5%. So that equals a probability of 0.025. Now, the probability that a plane ticket costs between $210 and $240. Well, that's between plus and minus 1 standard deviation. So there's a few different ways we could do this, right? The empirical rule tells us that's 68%. We could also add up your two 34s, right? 34% plus 34% gets you that 68%, or in probability form, it's 0.68. So that's your empirical rule. Now, question 5. What are the proofs for normal distribution? Right? So before you can use a z-score, you always have to prove normal distribution. So we have some proofs for means, and then we have proofs for proportions. Let's start off with the proofs for means. So your first proof is that you're told that the underlying population is normally distributed, bell-shaped, and sigma is given. And remember, sigma is your population standard deviation. If they give you S, if they give you your sample standard deviation, number 1 will not work. That first proof won't be true, and so you won't be able to prove based off of that one. You need sigma for that. The second proof that you could use, n is greater than or equal to 30, and sigma is given. Once again, it's sigma and not S. And n, little n, is your sample size. So if you take a sample of at least 30, and you know the population standard deviation, you can prove that your population is normally distributed. And again, if you prove that your population is normally distributed, that means that you are allowed to use a z-score. And if you can't make any of these proofs work, then you have to use a t-score. So proof number 3 is n is greater than 100. Right? If you take a large enough sample, your population can act like it's normally distributed. Right? So those are your 3 proofs. Now, for means, just one of them has to be true. Right? You can choose 1 or 2 or 3. If any of those are true, you have your proof. If none of them are true, again, that's when you use a t-score. Now, for proportions. Proportions are a little bit different than means. N times P is greater than or equal to 5, and N times 1 minus P is greater than or equal to 5. If one is true and the other is not, it is not normally distributed. You need both of those to have your proof. So again, N is your sample size, P is your proportion. So those are your proofs. So anytime that you need to show a sampling distribution, or when you are working on hypothesis testing and you need to prove in order to use a z-score, you need to remember to include these, right? You need one of your three means or both of your proportion proofs. So now the last part of this review, we're just going to go through a few symbols, a few variables, and identify them, right? Because you have these formula sheets with you, but if you don't know what's on the formula sheets, that it's not going to help you, right? So this first one, sigma squared. Sigma squared is your population variance. Sigma is your population standard deviation, right? So again, your standard deviation is the square root of your variance. Now, S squared, that's your sample variance. And S, that's what we found back in question number 2, that's your sample standard deviation. So if you have population data, you will be working with sigma squared and sigma. If you just have sample data, you will be working with S squared and S. So knowing what all of these mean will be really, really helpful when looking at that formula sheet. Now a few more. Big N, right? Capital N. That is your population size, right? So how many are there in the entire population? That's big N. That's capital N. Little n, lowercase n, that's your sample size. That's the number of observations in a sample. Now, an extra one that I haven't included here in this review is K, right? You guys just learned about K in chapter 19. K is your number of samples. So if you take 5 samples of 20 observations each, K is 5 because that's the number of samples that you took. N is 20 because that's how many observations are in each sample. Right, so N is sample size. Little n is sample size. Big N is population size. And K is the number of samples. Now a few more here. Mu. Mu is your population mean. Right? That's the average of all of the population data. Right? That's your population mean for mu. X bar, that's your sample mean. That is the average of a sample that you took. So again, if you know these symbols, if you know what they mean, what they stand for, it's going to be a lot easier to start filling in that formula sheet.